Alright guys, welcome to lesson 3 of our acid and base unit. So this lesson is going to talk about neutralization reactions, a little bit about electrolytes, and about our alternative theory of acid and bases. So let's start with electrolytes. So an electrolyte is a substance that conducts electrical current when it's dissolved in water because of those ions. That's the key thing there. Acids, bases, and salts are all electrolytes because they all dissolve in water and break into ions. A salt, not just table salt, but all salts, an ionic compound, so it's a metal and a non-metal, or a polyatomic ion. Our biggest one that comes to mind when people say salt is sodium chloride, but it could be any metal ionic compound, not just sodium chloride. All right, and here we have, in the image, we have a liquid with dissolved ions and some electrodes conducting electricity to show the flow there. So just a quick overview of what electrolytes are. There's also a great post from lesson 1 from Miss Anastasi in Google Classroom summarizing what electrolytes are. So now we're going to move into neutralization reactions. So a neutralization reaction is when we mix an acid and a base together. Think your classic vinegar and baking soda. So we have our acid plus our base. We get a salt and a water. This is a double replacement reaction. So we have, remember our alphabet, our A, B, C, D. They're all switching around, right? So if we look at this here, we have AB plus CD yields AD plus BC. So A is positive and C is positive because they're first. B is negative, D is negative because they're second. So our positives are basically going to switch their negative partners. So D and B, oh, let's fix this because I wrote this incorrectly when I typed this up. So this should be CB. There we go. So our D and our B are still negative, and our A and our C are still positive there. So a neutralization reaction, when something is neutral, the concentration of H plus ions or H3O plus, remember hydronium is the same as H plus ions when we're talking about pH and acids. So a neutral reaction, a neutral solution is when the concentration of H plus is equal to the concentration of OH minus. So let's look at some examples of these. So we're able to predict the products of these neutralization reactions because we know that double replacement, right? So we have hydrochloric acid, HCl, is being neutralized with sodium hydroxide. So if we look at our little formula right here, acid plus base is going to give us a salt and water. So we know that one of our products will be H2O, right? So we are left with our salt being NaCl. So just double replacement. We can go through and make sure that this is balanced, 2 hydrogens, 1 oxygen. So of course, we are a balanced reaction here. But let's look at it with a different acid and base. So we have sulfuric acid here. So this again is our acid, and potassium hydroxide. This is our base. Again, we're going to have a salt and water, right? So we're going to write our water. I'm going to write water as HOH this time just so we can visualize that it's the hydrogen from the acid and the OH from the base coming. So now we're left with potassium sulfate. All right, so potassium sulfate, we are going to have K2SO4. Let's make that a little bit smaller. Right, so that is our salt. Again, so we are able to predict the product. That's a big thing here with neutralization reactions, is that we're able to predict what the outcome is going to be because it is that double replacement reaction, and we're always going to have salt and water as a product. So let's look at some more practice. So if you guys could, pause the video here, take a second to work on these, and then come back when you're done to practice, and we will go over these. All right, so take a few seconds here, a few minutes, pause the video, and come back when you're ready. All right, so you should be coming back from unpausing the video after practicing these word problems. So let's take a look at these. So our first one, hydroiodic acid reacts with sodium hydroxide to form water and sodium iodide. So we were given the reactant. So we have a reactant, and we were given the product. So product and product. Write a balanced equation for this neutralization reaction. We were also told what the reaction type was. So let's start with our reactant. So hydroiodic acid. So we have hydrogen and iodine. Reacts with sodium hydroxide. And this gives us water plus sodium iodine. So NaI. All right, so, and is this balanced? Let's take a look. So we have two hydrogens, one oxygen, one. It looks like we're all balanced. All right, so let's take a look at the next one. So our next one, we have nitric acid is neutralized with zinc hydroxide. Predict the products of this neutralization reaction and write a balanced equation. So here we're predicting the products. The first one, the products were given to you. This one, they were not. So let's look at our reactants. So we have nitric acid. So we have HNO3, and we have zinc hydroxide. So zinc hydroxide is going to be this guy here. And let's remember our formula. Remember our A, B, C, D formula? So we're going to have A, B, C, D. So we know it's a neutralization reaction. So we know one of our products is going to be water, right? So let's do our little swapping here. So A and B, C and D. So A is going to take the place of C, and we're going to end up with AD, which is going to be HOH, right? And then B and C are going to swap. So C is going to take the place of A, and we're going to end up with zinc nitrate. Right, so this would be our AD, and this would be our CB if we're using our formula. Now let's check to see if this guy is balanced. And it looks like it is not. So I'm going to throw, see, we have two nitrates, so I'm going to throw a 2 over here to balance that. And it looks like we have two OHs, so I'm going to throw a 2 here, and we should be all good. So remember, sometimes you're going to be given problems where you're provided with the products. Other times you're going to be given problems where you're only given the reactants and you have to predict. Because this is a double displacement, it's easy for us to predict the the products. We just need to remember oxidation states. So we know what our subscripts are going to be, right? So keep that in mind. Practice these. If you need more practice with them, come to me if you would like more practice problems. Otherwise, there should be some like this in your Castle Learning later. So just a little bit of extra info, kind of like the last one. I gave you a little extra info slide. Neutralization reactions. This is also a little preamble to something we're going to talk about in a later unit. So we can break these reactions down into what's called a net ionic equation. So a net ionic equation shows only the chemical species that are directly involved in the reactions. We eliminate the spectator ions. So spectator ions, think of a sporting event, right? You have your fans in the audience, you have your players on the field. The fans are there. They're part of what's going on, but they're not actually playing the game, even though they still play an important role, right? Right now what we're going through, they're thinking about opening up sporting events, and it's just going to be the two teams on the field and no spectators. Imagine how that would be. Kind of a boring game. Those players enjoy the camaraderie that comes from the fans. So they play an important role in the process, but they're not directly involved with the game. That's your spectator ion. So they're ions that don't take part in the chemical reaction, and they're found both before and after. So let's look at our example here. So we have hydrochloric acid, so we have HCl reacting with sodium hydroxide, NaOH. So we know this is a neutralization reaction, and we're going to have sodium chloride and water as our products. So just to put things in some perspective, these are both aqueous. This is aqueous, and this is going to be a liquid for our sake now. So all of these being aqueous, these all dissociate, right? So they all break into their ions when dissolved in water. So we could rewrite this out in a little bit of a longer fashion, and we could have H plus Cl minus plus Na plus OH minus. And this gives us Na plus Cl minus plus water. Remember, water is a liquid, so it's not going to break apart. It's not going to dissociate. So now that we see everything broken up into its ionic form, we can go through and we can see who's the same on both sides. So I have an H plus on the left, but no H plus on the right. I have a Cl minus on the left, and I have a Cl minus on the right. So I'm going to cross those guys out. Those are spectators. Let's see, Na plus, I can cross those out as well. Those are also my spectator ions. OH minus on the left and no OH minus on the right. So they're never really reacting, the sodium and the chlorine. They're kind of just hanging out in the beginning, and then they're still hanging out there in the end. So really what's happening here is we have our H plus OH minus yielding H2O, right? So we just completely neglected the sodium and the chlorine because they're not really involved. They're kind of just there. So this is a net ionic equation. Again, this is not something you need to harp on right now. It's just a little bit of extra information and just kind of to expose you to some vocabulary before we move on into a unit where this is more prevalent. All right, so enough for neutralization. Let's talk about alternative acid-base theory, or Bronsted-Lowry theory. This is what we're working with here. We talked about Arrhenius acids and bases in lesson 1. So now we're going to talk about the Bronsted-Lowry theory. So this explains the behavior of weak acids and weak bases. According to the Bronsted-Lowry theory, an acid is defined as a chemical species capable of donating a proton or a hydrogen cation. Remember, cations are positive. So with an acid, it's giving that away, right? Or it's donating it. Bases, on the other hand, are defined as a chemical species capable of accepting a proton or hydrogen ion in the aqueous solution, right? So they're going to take it and they're going to accept it. Fun thing to remember here, we have bad. Oh, my pen's not working. Bad. So we have our bases accept and our acids donate. Right? Kind of like we talked about BARF and SNAP. This is just another acronym for you guys to remember, the Bronsted-Lowry. And then with Bronsted-Lowry acids and bases, they have what is called a conjugate pair. So they always contain the same elements, but the acid has an extra H involved. So they're just like opposite of one another. So if we look, so I put the bad acronym here for you guys too. So this is just something for you to remember. Just some graphics to work with the conjugate acid-base pairs with Bronsted-Lowry. We have, let's look at the diagram on the left that shows water reacting with hydrochloric acid, this one right here. So we have our water, which is a base in this situation. Remember, water is amphoteric, so it can behave as a base or as a acid. And I'm going to talk more about amphoteric compounds on the next slide, so bear with me. So water in this case is a base, and it's reacting with hydrochloric, which is an acid. And we end up with H3O plus and Cl minus at the end. So we have our base and our acid. What's happening is our acid here in hydrochloric acid is donating a hydrogen to water, right? So we look on the other side, H3O plus has an extra hydrogen. That's why it says acid 1, because it goes with base 1. Then if we look here, so this now lost its hydrogen, and that's where we're left with Cl minus. So those are the conjugate pairs. Notice how water and the hydronium ion go together, and the only difference is one hydrogen. HCl and Cl go together, and again, the only difference is one hydrogen. If you would like to see it in letters instead of in compounds, the graphic up here on the right is great as well. You have your Bronsted-Lowry acid, which is going to give away, it's going to donate the hydrogen to a Bronsted-Lowry base. And then it's going to have a conjugate base with one less hydrogen, whereas your Bronsted-Lowry base is going to have one more hydrogen in its conjugate acid. Right? So if you're ever confused on where something's going, just remember that Bronsted-Lowrys are bad. Bases accept, acids donate. All right, last slide for lesson 3, we have amphoteric compounds. So when you hear the word amphoteric, you hear that amph part, right? Like an amphibian, like our cute little frog buddy here. So an amphibian lives on land and water, so it's versatile, right? It can go in both situations, both ecosystems, right? So an amphoteric compound is a compound that reacts both as an acid and a base. So they have a transferable hydrogen that they could give away, and they also have an atom with a lone pair of electrons. Think about water. Remember, it's on that bent because we have available electrons up top, so we're in that bent shape. So water has hydrogens that it could throw away, but it also has spots on the oxygen for it to take something in. So when we look at water, it has a neutral pH, right? So the concentration of our OH is equal to the concentration of our H+. And we can write water as H2O or HOH. So don't freak out if you see it written either way. We're more familiar seeing it H2O, but it can be written as HOH as well. Okay, so when water behaves as a base, we said that bases accept hydrogens. So when water is reacting with HCl, it is behaving as a base. Hydrochloric acid is giving its hydrogen away, and water is there to pick it up. Whereas when water acts as an acid, water reacting with ammonia, it's actually going to give away its hydrogen, and we're going to get that ammonium ion with NH4 and OH-. So water works both ways. It works as an acceptor and it works as a donor, and that's what our amphoteric compounds are, right? Could go either way, depending on the situation and depending on what it's reacting with. All right, so you guys should have completed lessons 1 and 2. You should have completed your lesson 1 and 2 quiz on Google Classroom as well. If not, you need to contact us and we will get things situated for you all. And then keep an eye out for the next assignment that goes with this lesson. And as always, if you have any questions, comments, or concerns, please reach out to both of us. We are always available to help you guys when needed. All right, keep up the great work, and I'll see you for lesson 4.